So we finished up last time talking about why factorial designs are in general more powerful than one-way designs. Recall that in just a general study, right? So we had an example looking at self-reported arousal in response to 3 different types of films, right? And what we would have here with our one-way design, we have our differences that are systematic differences that are associated with film condition, right? So some people watch a happy film, some people watch a sad film, some people watch a fearful film, and across individuals we're just seeing, on average, are people reporting more emotional arousal to one type of film versus the other. In our one-way design, say we have 20 people in the sad, 20 people in the afraid, 20 people in the amusement, 20 people in the anger film. Systematic differences in arousal that we're seeing on average across these different films are going into our sum of squares or our variability for effect, and everything else gets thrown into error. Okay. Now, if we were to redo this study as a factorial design, looking at having 3 different conditions in terms of film, right? So we've got fear, amusement, and anger, different people watching each one of those films, but then go through and measure participant gender as a second factor. We would then have what type of design? Morgan, what type of design would we have here? 2 by 3, exactly. Right, so we've got a first factor with 2 levels, male, female. Second factor with 3 levels, fear, amusement, anger. And what we would have is this, our effect is going to contain condition, gender, and then the interaction of that, right? And what ended up happening is probably what we're going to get. We're probably going to get a stronger effect of condition, right? We're going to have a greater power to detect this effect of condition, because what we've done is we've also got systematic variability due to gender in the interaction. Even if these aren't clear, reliable effects, they're probably going to have some account for some variability in our data, right? Before, in the one-way design, these factors were getting thrown in the air, right? In our factorial design, we're systematically modeling these, and so Angela, what's going to happen to my error term in the factorial design versus the one-way? It's going to be smaller, right? And because in ANOVA, we're using the same error term, at least in our omnibus effects, to test everything. If our error term is smaller, what does that do to our test statistic, Rajiv? It makes it bigger, right? And if our test statistic's bigger, we have systematically bigger, we have more power to detect effects, okay? So this is a very nice thing about the factorial designs, but it starts to cause some complications conceptually in error terms that we're using for post hoc and follow-up tests and things along those lines. So talking about effect sizes for our factorial designs, we have our eta squared. Talked about eta squared before. Eta squared is just our sum of squares effect over the sum of squares total. Okay. Conceptually, Katie, how do we interpret eta squared? Remember? Okay, so yeah, that's what's going on. So what would our practical interpretation of that be? You're on the right track.
Variability with
Taking a look. Anybody help her out? Taking a look at the way this is how we're calculating eta squared. How would we interpret? How do we interpret eta squared?
percentages.
Yeah.
That's accounted for by the effect.
Exactly, right? So in our one-way design, we had talked about this as the proportion of variability in our whatever our outcome is that's attributable for these data that's attributable to our factor, right? And we can see this because this is just the systematic effect of the factor over the total. If we got a part over a total, that's a percentage or a proportion here. And so this is just a proportion of the total variability in these data, okay? So we can go through and calculate an eta squared for our factorial designs as well. We've got more than one factor, but what we can say is this is the proportion of variability in emotional arousal that's attributable to film condition for these data. Or if we were looking at our main effective gender, we could say this is the proportion of variability in our arousal ratings that's attributable to participant gender. Or we could say this is the proportion of variability for these in arousal that's attributable to the interaction of gender and film condition for these data. Okay, it's just a percentage of variability. Eta squared, very nice, very easy to interpret, but remember that our eta squared effects are a positively biased estimate of the population parameter, right? Stephanie, do you remember why we said that eta squared is a positively biased test statistic? Even if in the population this effect has zero relation with my outcome, absolutely none. Is my sum of squares going to be zero in the top when I'm actually working with data? No. It's going to be something, right? It's always going to be incrementally some number that's greater than zero just due to random chance, right? And so for our eta squared, we're just going to pick up some static, right? So even if the true population parameter is zero, it's still our actual point estimate of that effect. If we're calculating eta squared isn't going to be zero, it's going to be something greater than zero, right? And so we're concerned that eta squared is going to be positively biased estimate of the population effect. For these data, right, it's a nice descriptive statistic for the set that we have in our hand right now, but it's going to be positively biased for the population as a whole. When we transition into our factorial ANOVAs, we also have this issue where our eta squared is going to start to become systematically smaller with the incorporation of additional factors, okay? This is also going to start to become really a problem if we're not working on true randomized conditions. If we actually have, if we're working with some pre-existing factors, some quasi-experimental set where our factors are actually correlated with one another, what ends up happening, so in our one-way ANOVA we have the sum of squares for factor A, but in our 2x3 we have a unique effect for A, B, and then the interaction of those two. And so what ends up happening systematically over time is that sum of squares effect in the numerator, as we start adding other things, right? This is the unique effect explicitly for this factor. And as we start adding other things in there, that's probably going to shrink, right? Because in general, the systematic effect that we saw across condition might have at least some residual thing, some small relation with gender, right? And then, so this is going to start to get smaller. And so what ends up happening is we have a hard time comparing just eta squared across different studies using different designs, okay? And because as we start to add more factors in there, this unique effect that's attributable to whatever our factor is probably going to start to get incrementally smaller and smaller the more things we add in there. And so what we would expect on average is that our eta squared is going to be, for a given factor, is going to be smaller in larger designs than it would be in like a one-way design. Okay, people can start to see what's going on with this and our concern with eta squared. So what we have with the factorial design is our partial eta squared. Now partial eta squared is a little bit different because it's a partial coefficient. We would interpret this as the proportion of residual variance unaccounted for by other factors. For our partial eta squared, we have our sum of squares effect. So it's the same numerator, but in the denominator, we're dividing our sum of squares effect by the sum of squares of effect for our factor plus the error that we have left over. Okay, so now in a factorial design, for eta squared, we have the systematic in the denominator. We have the sum of squares total includes the sum of squares of effect of our effective interest. It includes the sum of squares for factor B. It includes the sum of squares of the interaction, and then the sum of squares error, right? That all goes into this. Here, we're just taking the sum of squares effect of interest over the sum of squares effect plus error. And Alex, which one of these statistics is going to have the smaller denominator? Yeah, right. Why?
Because in beta squared you're looking for total, but in factorial you're only looking at factor error, which is smaller than total.
Here we're partialing out variability, systematic variability that's due to our other factors and our interaction terms. So this is going to be systematically smaller, right? And if we're taking the same thing divided by a smaller piece of the pie, our effect is going to be larger, okay? And so now this is what makes this a little bit more difficult to try and interpret, because we're saying that this is the proportion of variability attributable to this factor that's not accounted for by other variables in the model, okay? So it's not the total. This is a nice, clean interpretation. Of all the outcome, this is the proportion of variability of all the outcome that's due to our factor. This is different. It's a partial coefficient. Things that are systematically related to other variables in our model are getting pulled out, and so we're interpreting partial eta squared as the proportion of variability, the proportion of variance unaccounted for by other factors. So everything else that's not attributable to sex or the interaction of that, this is the proportion of variability that's attributable to condition. Okay? And so wanting to be clear, I gave you all that effect size handout with, so there's lots of stuff and some of the technical stuff. Go through though that, take a look, because again, giving examples of how to interpret some of these effect sizes. So we would say, so in general, our partial eta squared useful for comparing effects across studies with different numbers of factors, okay? And also central to the calculation of power. What happens, Lauren, to partial eta squared in a one-way ANOVA? So for our factorial designs, which one of these is going to be bigger, eta squared or partial eta squared? Partial eta squared. What about in our one-way? What's that?
It'd be smaller then.
Not smaller. So if I take, in my one-way design, if I take sum of squares for my effect, and I divide by sum of squares effect plus sum of squares of error, what do I have?
What do you mean?
So what do I have left here in a one-way design?
Just
Yeah, just the total, right? Because in my one-way design, all the variability I have is due to my effect and my error, right? So what happens to partial eta squared in a one-way design between eta squared and partial eta squared?
I'm confused.
They're the same.
Oh, okay.
They're the same thing, right? If you calculate partial eta squared in a one-way design, or if you see partial eta for a one-way design, it's just eta squared, right? Because this is the total piece of the pie in a one-way design, right? I have my sum of squares effect, my sum of squares of error, and then my total, right? And my total is the combination of my sum of squares error and my sum of squares effect. Now in a factorial design where I have multiple factors, then this ends up being smaller, right? But this ends up, partial eta squared reduces to eta squared in a one-way design. And this is important for calculating power. If, Morgan, you had sent me an email about calculating G power and things like that. Were you able to figure out kind of what was going on
Now
with
I'm
that?
not so sure. I thought I did, but now that I'm reading, I'm not so sure.
Okay. Well, in that, it'll ask for partial eta squared as a way to get your F squared, right? Well, if you know that eta squared is the same thing as partial eta squared, it starts to sort of facilitate that a little bit, right? And so, again, with our partial eta squared, it's just harder to sort of make a clear interpretation or a practical interpretation of partial eta squared relative to eta squared, but better for comparing effect sizes, omnibus effects across different types of studies. Central for the calculation of power, right? So here's the direct relation between F and partial eta squared, but partial eta squared continues to be a positively biased estimate of the population effect. Okay. Questions about partial eta squared? All right. So just like before with our one-way design, our omega family of effects starts to become better population estimates. What ends up happening with our omega squareds, still a positively biased estimate of the population parameter. It's just a much less biased estimate than our eta squared and our partial eta squared. What we can do is we start to get complicated and start to incorporate more complex types of designs, with factorial designs and repeated measures designs. Starts to change a little bit how we would calculate our omega squareds. And again, omega squared generally assumes we have a balanced, relatively balanced design in order for these to be, in order for us to have reasonable confidence in these, okay? Couple of different ways to think about calculating omega squared. Over here is a general, if anybody's moving through Howell and following the Howell chapters, Howell talks about calculation of omega squared, partial omega squared in factorial designs using some of these things where your different error terms here are gonna be determined based on the type of design that you have. This is gets kind of bulky and complicated, but what we have, again, for designs that are balanced or nearly balanced, right? We end up with a number of effects that are for calculating omega squared. And again, if you go through and take a look at that handout, and this is what's difficult with this literature, there's like 7 different formulas for doing this. But if you get tricky and set up an Excel sheet and sort of work all those different formulas at the same time, they're almost always functionally equivalent. So instead of worrying about some of the stuff that Howell's given you, this a formula you can use to calculate omega squared. Here, formula to calculate partial omega squared. Okay. Again, we would interpret these as the same way as we do omega squared eta squared and partial eta squared. It's just these we would interpret not as the proportion of variability in these data, but our estimate of the proportion of variability that the factor accounts for in the outcome within the population. Okay, so thinking about these more as population statistics as descriptives for this given sample. So still positively biased, but much less so. Okay, and so here we're looking at our degrees of freedom effect multiplied by our F statistic minus 1, and then in the denominator we just have degrees of freedom for factor A, test statistic factor A, B, test statistic factor B, so on and so forth for however many factors that we have in that design. Partial omega squared, a little bit more straightforward. Degrees of freedom of effect times our F statistic minus 1 over the same thing plus total number of people in our sample. Okay. And so if we know that what's going to be bigger, partial eta squared or eta squared? What do you think, Katie? Partial is going to be bigger, right? Partial eta squared going to be bigger than eta squared, except for in what case? One-way design, then they're going to be the same thing, right? Same thing with omega squared and partial omega squared. What's going to be bigger in general when we're comparing, let's say, omega squared and eta squared? Right, because again, it's a positively biased estimate. Same thing with partial omega squared and partial eta squared. Partial omega squared will always be smaller. Partial eta squared will always be bigger because we're concerned about inflation of the test statistic with eta squared and partial eta squared. Okay. People kind of wrapping their head around this a little bit. Cool. Okay. Effect size, if we want to calculate effect sizes on omega squared, we can do that. Again, easy, calculating 90% confidence intervals, we go through and do that. Again, I've started to become less enthusiastic about this. It just doesn't seem to, we often just don't care about our omnibus effects all that much. So less emphasis on this, but if you wanted to do it, this is how you go through and do it. Very easy, just like we've been doing with things translated back into that. And so eta squared and omega squared, proportion of total variability attributable to a factor. We're looking at, if we went through and were to calculate our eta squared, at least, for each one of our factors, that would sum to our total effect that we're accounting for. Conservative estimate, in that this is always going to be smaller than the partial coefficient. Partial eta squared, partial omega squared won't sum up to our total because we're starting to partial things out. And again, sort of primary benefit here, useful for comparing a certain factor across designs of different size and different factors and things along those lines. Okay, and again, these are particularly your eta squared and omega squared, using that as to calculate your power analyses and things like that. Questions? All right. In G power, if we wanted to run a power analysis for a factorial design, what we would want to do is take a look at the power to detect an effect of a specific factor. So we choose F family of tests. We're looking at fixed effects, specific main effects and interactions. What we're doing is we're powering specific effects within this design. We're doing a priori. If we hit input determine, we go through here. We just hit direct and put in whatever we calculate partial eta squared for. It's going to calculate our effect size, move that back over there. Alpha level power, we're generally powering this to 0.8. Numerator degrees of freedom, how many levels to our factor there is, -1, right? Number of groups that we have total, and just running through and calculating all of this, right? So if we have 3 levels to our factor, how many, what type of, what design is this? If we have 6 groups, we have 3 levels to our first factor, how many levels do we have to our other factor? 2, this is just our 2x3 design, okay? And so then we would go through, and so, yikes. Yeah, this is a math, this would be, it's partial eta squared of 0.33 is huge. I mean, if you take a look, we're saying total sample size is 24. How many people in each cell? 4, yeah. So, I mean, this is not a realistic output for a power analysis, but sort of kind of what we got there. Questions about this? All right, now we get into real important stuff, okay? So we go through, actually let's wait on that. Let's jump into a screening. So open up your data set for the 2x2 expressive behavior. And you can pull up that the handout for that as well. So we've got a screening, and then we've got just the actual test on this. So first thing we want to do is take a look and see if our data are reasonably consistent with the assumptions of Factorial ANOVA. What are our assumptions that we need to be concerned about as we're running through our screening? What do you think, Rajiv?
First, check if we have any missing data or not.
Okay, missing data. outlying or values that don't make any sense, right? So we want to go through and take a look at those. What about in terms of assumptions of our statistical test? Stephanie, what do you think?
We can look at like the scheme for
What's that?
the scheme for choices, like the distribution.
Okay, so we want to take a look at the distribution of our scores within each one of our cells, right? What is our normality assumption with these means-based tests? Do we need to see normality in our actual data? Alex, you're shaking your head. No, why is that?
The population is certain, like the data.
Not even the population, because we can run ANOVAs on data that's skewed in the population. What's our normality assumption in our means-based test refer to? What is it? What's that? Variance? Well, that's another one. We have to want to see homogeneity of variance. We're assuming homogeneity of variance in the population, right? So we're saying that this population and this population and this population, we're expecting their means to differ, right? But we're expecting their variance to be the same. What's our normality assumption? This is important when we're going through an interview. What is it? Distribution of sample means, right? So it doesn't matter if our necessarily if our observed scores aren't perfectly normal. We really actually, because that's not our assumption, right? What we're assuming is if we were to take repeated samples of this size and then plot out the means, eventually that distribution of sample means would be normal, okay? And under what two conditions do we see distribution of sample means start to approach normality? When the population is normal, right? So whatever we're measuring, if that has a normal distribution in the population, we would expect it distribution of sample means to hit.
And then is it 30 samples?
It's a continuous, it's kind of a
Okay.
sort of a logarithmic function, right? But reasonably large sample sizes. As our sample sizes start to get larger and larger, even if we have kind of ugly distributions in our data, we're still pretty good, because even if I take a very skewed variable and I resample that with replacement again and again and again, even that skewed distribution of sample means for that skewed distribution is still going to approach normality, right? So when we're going through and taking a look, things we want to be thinking about is, one, what are we looking at in population? Is this something that I would expect to be normally distributed? And how many people are in my cells? Do I have another, because if I got a large cell size, I'm pretty good, right? But if I don't, and I got wonky data and other sorts of things, then I start to become more concerned that I violated some sort of assumption, okay? So we've got accuracy, plausibility, missing data, we've got homogeneity of variance, we've got normality, and our normality assumption is normality and distribution of sample means. What other things do we want to be taking a look at in our screener? We want to be making sure we don't have any outliers, right? We don't have any stuff going way out. And then the other thing too is independence, right? We want to make sure that people in this cell aren't influenced by people in another cell, aren't influenced by people in another cell. We can't screen for that based on our observed data. That's a design issue that you would want to go through and make sure that no one's looking on anybody else's paper. Everybody's score is independent of everybody else's score. Okay? So, what we want to do first, if we pop this open, so we've got in our data here, we have what we're interested in figuring out here is whether or not what the impact of film condition and instruction condition is on people's behavioral coding of expressive behavior. So what we do, we bring people in, we sit them down, and we have two film conditions, whether they're to watch a funny film or a sad film. And across those conditions, we either tell people to just watch the film naturally, or we tell them to inhibit and restrict all of their behavior. Okay? And then what we do is when they watch the film, we record them as they're watching, and then have someone go through and make a behavioral code on the extent to which they're expressing behavior. This is just a global rating of global emotional expression. Okay, so what kind of design do we have here? Okay, it's a 2 by 2. Okay, and so how many cells do we have? 4, right? And so when we're screening, how many groups do we have to look at? 4, right? Need to go through and take a look at all 4 of these cells. And so in these data, we've got our subject, film, instruction, and then what I've done is I have just added a condition variable. And so if you look, everybody who has watched the SAD film and express, they have a condition code 1, SAD inhibit, condition code 2, humor express 3, and inhibit or humor inhibit is 4. Why have I gone through and done this? Yeah, right. So I can go through and I can split this file by the 4 groups and look at these individually. Okay. This is something that I've coded in for this example because it's nice to just have a variable that identifies each one of your individual cells. Because what we need to do, just like we did between groups, went through with the between subject samples t-test, had to split into group 1 and group 2. Here starts to get a little more confusing because you've got multiple cells. Each one of these cells is a population. Each one of these cells represents a hypothetical population out there in the universe that we have to go through and make sure that we're reasonably accounting for. Okay, so what we're going to do is we're going to go to data, split file, and we're going to organize groups, organize output by groups, and then we're going to take our condition variable that sets up our 4 different groups and separates those. You guys can hit paste. I'm going to hit OK. All right, and now that we've split that file up, what I'm going to do is I'm going to go analyze descriptives. And I'm going to look at my expression rate because that's my dependent variable, that's my outcome. I'm going to pop that over there. I'm going to save standardized values as variables, and then in options, I'm going to ask for skew and kurtosis values, and I'm going to click variance here as well because this starts to become sort of relevant as we're going through and screening things. Okay. So we're going to go through and we're going to hit continue. You guys hit paste. I'll just sort of run this. Okay. What do we got going on here in terms of our, actually, you know what I should have done first? Yeah. All right. Whoops. Looks like we had three variables that didn't have an express. We must have lost video for that, so we're going to go through and delete those. Okay. I got ahead of myself. Didn't go through, make sure to take a look at my if I had appropriate values and any missing data. So now I have to go back through, split file again. So make sure we split that. Clear that out, and then run that again. Okay, now we're in business. All right, help me out. What are we seeing with these data?
Relatively equal cell sizes.
Okay, so we're doing pretty good in terms of cell size, right? So we're happy about that. What's that?
Relatively large too.
Yeah, right. And so this is gonna help us out in terms of a lot of our concerns. If any concerns about normality, right? We've got clearly large enough cells to start to alleviate concerns if we happen to have wonky distributions in our data. Does it look like we have wonky distributions in our data, at least based on our indices here? Not too bad, not too bad, okay? So we've got, if we go through, we take a look, cell sizes are all pretty large and reasonably similar, so we're happy about that. Our values are within reasonable range, right? We've got a 1 to 5 scale that we're rating things on. Our skew's looking all right. Kurtosis is looking all right, at least in terms of absolute values. Okay. What's the one other thing we might want to take a look at and start thinking about here at this stage of the game? Yeah. What about our variance, Angela? Right. Okay. So in general, with these, we're going to run through and run our Levine's test. But in general, what we're looking for is rule of thumb, and again, take this with a grain of salt, ratio of your highest to lowest variance across your cells, 4-to-1 ratio. If we start to exceed that, we start to become concerned about whether or not this is going to be robust, particularly if we have unequal sample sizes. Now we've got relatively equal sample sizes here, so we're better off, but still wanting to go through and take a look at those variance estimates. And so I requested variance in here, right? And you want to make sure you're looking at ratios of variances, not of standard deviations. Smallest variance is 0.347, and our largest 1.152. So what's my ratio there? Morgan, I see you calculating it.
Sorry, I was just trying to look at what the maximum variance would be for that ratio for the 4-to-1.
Well, what happens is we take 1.152 and divide it by 0.347.
I didn't do that. 3.3.
3.3, okay. So our ratio is about 3.3 to 1. So it's not quite at sort of what we would say our limit was, but it's certainly different, right? And certainly something that we would want to take into consideration. Now, this is offset by the fact that we, at this point, we have reasonably equal sample sizes, but still starting to become concerned, right? And so what it looks like is, we don't want to just think about these as numbers, right? We want to think about, like, what's the phenomenon we're actually taking a look at. If we think about this, it looks like 4 people who were instructed to inhibit their expression in response to a sadness eliciting film, we're seeing much less variability in that group of individuals than we are for individuals who are watching a humorous film and told to restrict their expressive behavior. And this kind of makes sense, right? If I show you a sad film and I say, hey, don't act like you're not feeling anything, we might expect less to slip through, depending on how intense that sad film is, as opposed to a funny film where things are happening that are sort of unexpected and like things start to slip out, right? So we're seeing more variability here than that. These are always, always, always important things to think about, not just saying this number is bigger than this number. What does this actually reflect in terms of, okay? So, we're not terribly concerned quite yet. But what we want to go through now and do is go and take a look at our distribution. So what I'm going to do is I'm just going to go through and sort that, because that's going to take off that split. Go to descriptives, explore. We're going to put expression rating as my dependent, condition as my factor. Put subject number down into the labels here. I go to my plots, I'm gonna ask for histograms, and then you guys are gonna hit paste, I'll hit OK. Just gonna think about things for a moment. There we go. I didn't know we need a supercomputer to run SPSS these days. All right, so valuable statistics and things like that going on up here, but we've kind of looked at most of the stuff we'd be interested in. Want to go through and start taking a look at our distributions, right? Histograms, not looking too bad. I mean, we've only got a 5-point scale here, so there's only so much skew that you can have. But we're definitely seeing, for the sadness express, not a lot of expressive behavior skewing up into high levels of expression. Same thing, even less. Remember our sadness inhibit, this was the one where we had less variability, and we're seeing that 3 is our top point here. But they're both kind of skewed in the same position, in the same general direction. Something, so humor express, a little more variability there, and then humor inhibit, again, most people are not expressing a whole lot, but then sort of drifting out, skewing the other way. And so again, one of the things we want to be careful about when we're running our screenings, if you think back to the issues that we ran into with our independent sample t-test, same issues come up here, right? We're generally robust with our means-based tests unless we start getting clear evidence of homogeneity variance with different sample sizes, right? Or we have non-normal distributions in the opposite direction, right? So go back through and revisit that independent sample t-test lecture, and sort of when, and this is part of that Bonneau article talking about when we're not robust, right? And generally it happens when we're doubling down on violations. Here, it looks like we might suspect that we have differences in our in variance across these populations, but we've got reasonably similar sample cell sizes. We've got large cell sizes. And so based on these histograms, are we concerned about violations of our normality assumption, Stephanie? And is our assumption about the normality of our observed data or something else?
The
distribution of sample means, right? And so I probably wouldn't say that expressive behavior in people exposed to sad or humorous stimuli is going to be normal. I don't think that variable is normally distributed in the population, because most people are going to do a pretty good job. Some people are going to leak. We're always going to have a skewed distribution. But what's our saving grace in this design here? Yeah, what is that one? Large sample size. Because even if we're working with a variable that doesn't have a normal distribution in the population, as long as our cell size is reasonably large, distribution of sample means is still going to be normal, and so we're not too worried about it. Okay. So normality assumptions. If I was doing the screening, I might describe that at least for 3 of our cells, it looks like we kind of have something that's looking like a somewhat positively skewed distribution. Not bad, right? But a little bit. Our humor express is a little bit more normal, but I wouldn't say that we have clearly different shapes that are problematic here. We have a large sample size. Our box and whisker plot isn't looking great, right? Alex, what do we see in here with the box and whisker plot? Means or
Or medium, sorry.
medians, right? So we've got, what looks to be clear, some, what we would expect to be kind of positive skew across these, right? We've got an interesting, these two graphs look almost identical except for what? Well,
Like
the
all
red,
variability happening
right, so we've got more people leaking levels of expressive behavior in the humor inhibit. What else is going on here about across these two? Where's our medians? Median here is 1, median here is 2, right? It's just that my median is the same value for my SAD inhibit. My median value is the same value as my first quartile, right? Here, my median value is the same as my third quartile, right? And so we've got some differences in our medians. Humor inhibit's the only one we're starting to get values falling more than 1.5 times uniquartile range out. But again, we're only working with a 1 to 5 scale, so there's only so much out, at least in terms of our. And so this is the thing. I mean, we're treating these data as continuous. Are these continuous data? No, they're at best ordered categorical, right? And so one of these things you want to keep in the back of your mind as you're thinking about things. Okay. So we go through thinking about some of that stuff, and then wanting to go through, turn our split file back on, and go up and go analyze descriptives. Take a look at our z-scores, not z-scoring our z-scores, that's take off skew, kurtosis, variance, all that stuff. Continue and hit OK. All right. And what are we looking at here, Katie? Yeah, right. And are we seeing anything that we're hugely concerned about? What's that? Yeah, probably not too terribly concerned, right? I mean, there are things to note, right? In our sadness express condition, we've got people who are about 3 standard deviations above the mean. For sadness inhibit, 2.5. This is actually looking not too bad. For our humor inhibit, we've got people scoring over 3 standard deviations above the mean, right? And so when I'm running my when I'm running my screening, I might go down through and start to take a look at, that example that I had given you, I had sort of highlighted, so there was one person that was a little above 2 standard deviations. Not that someone above 2 standard deviations is necessarily an outlier, it's just for that data. It was someone who was a little bit high and sort of notable, so wanted to at least acknowledge that. Here, we've got I might make a note that I got one person in my humor inhibit condition who's 3 standard deviations above the mean. What's that, Alex, what's that telling us about that person? What's that?
That they might be an outlier?
Maybe, but I'm not too concerned, because it's not like we've got someone who's like, 7 units beyond anybody else in the thing. Conceptually, what's going on with this person? Given what we're doing in these data. So this is someone who was watching a humorous film, and we told them not to express their emotion, and what did they do anyway?
They didn't.
Okay, right. And so basically, again, always wanting to think about, this isn't just a number, right? This isn't 2 standard deviations, like what's actually going on here? We've got someone who didn't follow directions or couldn't follow directions, right? Now, the question is, do I get rid of that person? Well, I don't know, right? If I tell people if I think about normal human behavior and I tell people not to express their emotions, some people are gonna be more successful at that than others, right? This person is certainly scoring higher than we would expect given the sample mean, but is this person a representative individual in the population of people who we might try to tell to inhibit their expression in response to something funny? Yeah, it's one person. We've got a pretty large sample. I probably wouldn't be too concerned about that one individual. Now, if this was my study, I might want to go back through and double check, right? And make sure that this person was even like trying to do anything, right? Because if they just clearly weren't following the instructions, then we'll throw them out, right? If it was clear that they got confused or forgot or whatever, right? But from a statistical standpoint, conceptual standpoint, assuming that this person got the instructions and gave it their best and just wasn't very good at it, I still probably wouldn't want to take them out, right? Because otherwise it feels like I'm putting my finger on the scale with stuff. We've got someone in the sadness expressed that's expressing, so we got someone who just really got caught up with that sad film, right? This person right here, so sadness expressed, someone's really upset by that and expressed that highly, right? So I might want to sort of make note of that person. And then we've got a couple people in the sadness inhibit that are kind of, a couple of cases that are reporting kind of high levels. It looks like people in the humor express, we don't have anybody who's doing anything, so I don't think I need to talk about any of that there. But this is the type of thing I'm wanting you all to do in your screen. So to take, relative to this, do we have people who are problematic, demonstrating extreme values? If they are, is this someone problematic? Would you recommend that they eliminate that person? Would you say that it's fine, it's probably not gonna have a big issue? In this case, we've got a couple things going for us. One, we've got big cell sizes, so this person isn't gonna probably throw our whole thing off. Two, our scale is a 1 to 5 scale. I mean, there's only so much that people can be way outside on that. And 3, all of these, if we go back through and we take a look, remain continuous members of the distribution. Right, if we look at our histograms, now if I had everybody scoring 1 or 2, and then I had another person scoring a 5, then I might be a little more concerned about that. There is something odd going here, but it looks like people were just on a continuous spectrum of expression, so it's not too bad, right? When I start to get worried is when I start to see gaps in that distribution, right? When there are big holes and someone's sort of way out on the end on either way, and then I might start worrying about problems there. But overall, for this, what's our final conclusion on where we're at with our assumptions here? What do you think, Maureen? What's that?
Proceed with analysis?
Yeah, I think so, right? I mean, we've got we've got large cell sizes, we've got relatively equal cell sizes. It looks like we have some data that are kind of skewed, right? But not terribly so, so that I wouldn't be concerned with violations of my assumptions of normality in my sampling distribution. Maybe a couple of people we might have some questions about whether or not they're able to reasonably follow instructions in this design. What's the only thing that, at least at this point, I might want to have an eye out for? Do you remember? What do you think, Rajiv? Remember when we were back calculating ratios? What's that?
Give the variance.
The variance, right? I mean, I don't know, we're gonna run our Levine's test, right? And Levine's test might, I mean, we've got quite a few people in the sample, right? Which Levine's test is gonna be start to become increasingly sensitive the more people that we have. But we've got people who've got a 3.3 to 1 ratio of the highest to smallest variances, which is certainly something worth noting, right? And so that's something that we might wanna keep an eye out for, okay? People comfortable with screening on this? Cool. All right. And so then, at this juncture, then it's easy. Then we're just going to go through and say we're going to proceed. So keeping an eye out on that variance issue. So what we're going to do is we're going to analyze general linear model, univariate, and so for our dependent variable is going to be expression rating. Our fixed factors are going to be our film condition and our instruction condition. Okay. We're not going to have random variables or random factors in this. We don't have any covariates. We're not going to weight this by any numbers, so we're good there. What we want to do now is, if you can go through, we're going to have a full factorial model, so we'll just leave that. If you wanted to get fancy, you could start playing around there, but we won't worry about that right now. Contrasts, we're not going to worry about those quite yet. Post hocs, don't do this. Options, though, we're going to go through and we're going to ask for marginal means for film instruction and then my interaction. I'm going to ask for descriptives. I'm going to ask for estimates of effect size, homogeneity of variance tests, and I think that's good. Hit continue, and you all can hit paste. I'm going to just hit OK. All right. So a lot of this we should already know, right? So we've got 91 people in the amusement or sadness film, 898 watching the amusement. This starts to become important because this will start to have impacts on a couple of things we're going to be doing. Same thing, 94 who were told to inhibit expression, 95 who were allowed to withhold or instructed to withhold. What are these cell sizes referring to? These are main effects or interactions. Someone mumbled main effects. If you did, you should shout it out probably. Yes, because you're right. These are main effects, right? Main effect of sadness and amusement. Who expressed more? People who watch the sadness film or the amusement film, regardless of expression condition. Express. Who expressed more? Those people who were allowed to express or who were instructed to withhold, regardless of what film they watched. These are your ends for your main effects. These here are your individual cells, right? So we've got sadness express, sadness withhold, amusement express, amusement withhold, your means for each of those, standard deviations for each of those. These are all things that you've already taken a look at in your individual cells, but this is where, in your descriptors, where you're getting this in your factorial design. Okay? Then we've got our Levine's test. So Sam's gone, and so like everybody's never Levine's test. And so what does that tell us? Right? It suggests to us that we may have a problem with unequal variances, which we already kind of suspected based on just looking at our ratios, right? And so this starts to now have impact in terms of how we're going to go about and start probing things. This is a big stop sign in the road and trying to figure out what am I going to do with this. If you have a significant Levine's test, you're going to start to think, well, maybe I might have to start using a different approach than just pulling things off my error terms, my overall ANOVA table. with a sample like this, right? So we've got almost 200 people, which is a pretty big 2x2 design, right? And so I might be a little bit concerned, maybe that my Levine's test is a little bit sensitive, but if I go back through, if I see my ratio to largest to smallest exceeds 3, it's not at that point where I'm just gonna start to have serious reservations about robustness of my test, but it's enough for me to say, yeah, I should probably be not just pulling error terms out of my ANOVA table and assuming that that's gonna be a reasonable approach, okay? So, jump down, our next table after our Levine's is our tested between subjects effects, and what do we see going on here? So I'll help you out because this is a little bit confusing, but important to know. So we've got more rows in our ANOVA table here than we do when we went through and calculated stuff by hand, right? Our corrected model here, this is your sum of squares cells, okay? We don't put this into our sort of classic ANOVA table, but SPSS is going to give it to you. Sum of squares corrected model is your sum of squares cells. This is the sum of squares for your main effects and your interactions, right? Classic ANOVA table splits this out. This is a computational number, but SPSS gives it to you here. Your intercept, your sum of squares intercept, is the test of your intercept, is tested the main effect of whether or not you're, is it tested the grand mean, right? So is my overall mean value in these data greater than 0? It's not a useful thing, right? But it's part of the calculation stuff, and it starts to become when you need certain types of information that will become important down the road, but we can go ahead and get rid of that and ignore that, okay? Then we have our effective film, our effective instruction, and our effective film by instruction, okay? This is the stuff that maps onto our classic ANOVA table. We've got our sum of squares error here, and then we've got our total. Total is your total sum of squares that includes your intercept, okay? But again, are we interested in the intercept? No, scratch that out. What we want to look at in terms of your corrected total, or what we're wanting to look at in terms of your total sums of squares is your sum of squares corrected total down here. And you can see that if you add 27, 27, 3, and 165, this is what you'll get, right? If you start to become confused and can't remember which one of these to use, remember that your sums of squares effect and your sums of squares error should always add up to your sums of squares total. This is just other stuff going on that you don't need to worry about. Know what it is, but know that this isn't part of your regular interpretations. Yeah?
What does take 3 sum of squares mean?
Depending on how you're putting together, remember when we went through and had that like full factorial model and things like that, under certain conditions, you may choose a different type of sums of squares.
This is like a GLM thing.
Yeah, and it's having to do with different types of how you're setting up your model and things like that. I'm going to save you from getting into the nuts and bolts of all of that. The type 3 sums of squares is going to be kind of your standard thing. If you were to change that, you would want to have a good reason for sort of saying this is why we're changing stuff. All right, so now that we've got our table squared away, someone help me out. Stephanie, what are we seeing in terms of our effects? What are we seeing here? What's that? Yeah. So what do we got?
We see that the main effect for film is significant.
Mm-hmm. Suggesting what?
That there's a significant difference in expression based on film.
Exactly. So regardless of what instruction people were in, instruction condition people were in, people watching one film tend to express more than the other film, right? What do we have on the next one? So regardless of whether or not people were watching sad or amusing films, people in one of these instruction conditions were reporting higher levels of expressive behavior than the other. And then what about our interaction term here?
It is not significant for the first.
Right? So it's looking, it's marginal, right? And I don't know that I would necessarily disregard that, right? Now we've got a pretty big sample size, right? So normally not having sort of clear concerns about power, but we're kind of right there on that edge, right? And if I take a look at my effect size, remember sort of for partial eta squared, small effect is 0.01, I think, right? So we're kind of, I mean, we're at least meeting threshold for a small effect, right? So this might be something that I might be interested in exploring further, okay? And so down here, these are your marginal means. These are just adjusted means. I just like printing these out because it gives me a nice snapshot. I can just easily say. So given that we only have 2 levels to each factor, Angeline, what would you guess what's the interpretation you would guess we would make based on the main effective film? Just by eyeballing those marginal means. What does your main effective film tell you? That there's a difference. And how many levels do we have in this factor? So there's a difference. How many directions can that go? Okay. And so if I just look at this, how am I going to interpret that main effect of film condition? Yeah, right. This is what's beautiful about having 2 levels to a factor, is it makes interpretation pretty easy, right? Are these, and I guess I should be going down through, and I would look at so for the mean of my sadness and the mean of my amusement, right? Is there a reliable difference between those two? What do you think, Morgan? Yeah, right? Because my effect is significant. If that's significant, it says those two are different. And if I just look at the means and see which one is higher, I know what's going on with that effect, right? Same thing for my main effect of instruction. What's going on with my main effect of instruction? There's a little bit, if I go through and I look at the mean for expression, the mean for withhold, what's going on with that? Yeah, and that ended up being kind of interesting that they worked out that way. And so what's going on conceptually here?
Let me correct the measure, right?
Yeah.
Sorry, on my thing there, the tables are backwards.
Oh,
so
okay.
But there's some difference.
Right. So, and specifically, people who are allowed to express or expressing more expressive behavior than people who are instructed to inhibit, right? Now, when we get into our interaction effect, we didn't quite get there, but we might want to explore, we will explore a little bit more, right? But in general, what would, Katie, this interaction, if we decide that this is statistically reliable and we want to explore this further, what would be our interpretation here?
People who are assignments express more than assignments for food, and people in their amusement express more than amusement.
Okay, maybe, right? But this starts to get a little bit difficult because there's a number of different ways that we could tease this out, right? In general, right, we would say that differences in expressive behavior across film condition are dependent on sort of instruction, or differences in expression across people who are withholding and naturally expressing emotion is dependent on what film they're watching, right? but we need to dig into this a little bit more to go through and take a look at some of that stuff. Okay. Last thing we're gonna do here, wanna go through and calculate some effect sizes, right? Do we need to calculate partial eta squared? What's that? Yeah, no, it's right there. If SPSS gives it to you, don't hand calculate it, because it's just easier to pull it off of there, right? So we've already got partial eta squared. And how would we calculate eta squared? Is eta squared hard? No, eta squared is easy, right? We would just take our sum of squares for film divided by our corrected total, right? And that's what gives us our eta squared for the film. Eta squared for instruction is our sum of squares here, divided by our total. Good to go, right? What starts to get a little more challenging, though, is if we want to start calculating omega squares. If we calculate omega squared, omega squared is going to be degrees of freedom for our effect times our F minus 1 over degrees of freedom for A times F of A minus 1 plus degree of freedom for B times F of B minus 1, and so on and so on. Okay. So if we want to calculate omega squared for film, okay, what's our degrees of freedom effect for film? 1. Okay. Minus, what's our F for film? 30.684 minus 1. No, minus.
No, the degrees of freedom times that.
Oh, whoops. Yeah, sorry about that. Good catch, thank you.
Also in the denominator, don't we need to add n?
What's that?
Do we need to add an n in the denominator, and I did not see that.
Oh, yeah, it's plus
Do you remember talking about that?
and down at the end.
Got it.
Okay. Good, you guys are keeping me honest. You were fantastic. Okay, so there we got our numerator, all right? And now in the denominator, we're just going to systematically go through and add up degrees of freedom in our individual effects. So we've got 1 times 30.684 minus 1 plus 1 times 30.416 minus 1 plus 1 times 3.488 minus 1 plus 189. So people see what we did there? We just stepped through all this. And so this is how this is going to change depending if we had a 2 by 2 by 2, then we'd have a whole nother thing to add on there at the end, right? If we run this out, we're going to get an omega squared of 0.118. And if we were to calculate eta squared, that's going to be our degrees of freedom, or our sum of squares. No, what is this? Did I already calculate that? No. Okay, yeah, no, our sum of squares effect is going to be 27.487 over our sum of squares total is 22.286. And give us eta squared of 0.1, or excuse me, 0.24. Accounting for over 100% of the variance. Okay. So see what we've got here is our eta squared is pretty easy, right? Someone tell me how we would interpret eta squared for these data. Yeah, right. Pretty sort of, we'd say sort of the film condition, whether or not people were watching a amusing or a sad film, is accounting for about almost 12.5% of the variability in expressive behavior for these data. Okay. And what happened with our omega squared? Is it bigger or smaller, Rajiv?
Or omega squared?
Our omega squared.
Smaller.
It's smaller, right? Because remember, this is a population-based statistic. Our eta squared is too big. It's positively biased. And we can see our omega squared is smaller, not by a whole lot, but it is less, right? And so we would say, maybe our interpretation here would be, we expect that film condition accounts for close to 12% of the variability in expressive behavior in the larger population, or something like that. Omega squared is going to be our population statistic. Okay, people comfortable with that? All right, we can also calculate partial omega squared. This is going to be a little bit more straightforward. This is going to be our degrees of freedom effect. Oops. Degrees of freedom effect times F minus 1 over degrees of freedom effect over F that we're looking at minus 1 plus N. In this case, omega squared is going to be 30.684 minus 1, right? Multiplied by degrees of freedom effect is going to be just 1, so we can drop that out, over 30.684 minus 1 plus 189 is going to give us a partial a squared of 136. If we look at our partial eta squared for film is 0.142. Our partial omega squared is smaller, right? 0.136 because it's a more conservative estimate, has less positive bias. We would interpret our partial eta squared saying that within these data, film condition accounts for about 14% of the residual variance not attributable to instruction condition and their interaction. For omega squared, we would say that we would expect film condition to account for about 13.5% of the variability in expressive, the residual variability in expressive behavior not accounted for by instruction condition and their interaction. Because that's that other stuff. With our partial coefficients, we're taking variability attributable to other stuff, taking it out, putting it elsewhere, and then making our interpretations from there. Okay. People comfortable with calculating omega squared, partial omega squared off of based on pulling values out of this? We're going to come back to this example, but let's jump into real quick. Okay, let's run a real quick on this second set where we're looking at this trauma beliefs data set. Okay. Just to give us a little bit of a different look for the trauma beliefs. So what we're going to do here is we're not gonna fool around with screening. We go through, so we're missing class on a bunch of this stuff, so I'm just gonna nuke that. And then we're missing sort of input on one of those people, so I'm gonna nuke that. Okay, so we got a full data set here, right? And normally we would go through and screen and do all that stuff. But what we have here, a little bit different situation. What we have is some data from the lab that we're looking at trauma beliefs, right? Beliefs people have about trauma. I touched on this in that tenure talk that I had given that you all were there, so hopefully this is going to ring some bells. What we have is 3 different groups, right? We got 3 different types of groups that people have fallen into based on their endorsed beliefs about trauma. And what we want to do is we want to see whether or not these groups are systematically different in terms of positive affect and negative affect, right? So we want to see if people across these different groups are reporting higher levels of positive and negative affect, but we also want to account for participant gender, and so we're going to include that in there. So we've got a 2x3 design that we're going to go through and test on 2 different outcome variables here. Okay. And so what we're going to do is we're going to go analyze general linear model univariate, okay? And we're going to have our dependent variable for our first one is going to be positive affect, and then we're going to have gender and class as our fixed factors. We're going to go to options. I'm just going to have it give us our marginal means, descriptives, not observed power, effect size, homogeneity of variance, and then that's looking pretty good. I'm going to hit continue there, and I'm going to go through and I'm just going to paste this into a syntax file, because then what I can do is just highlight the whole thing, paste that down, there. Now I've got my second model. Okay, people see what I did there? Yeah, just change my outcome variable. Everything else is the same across this. So, this up, close that down. All right. We go through, run this. First thing I've got going on here, so take a look, it looks like I've got unbalanced cells, right? I've got large cells, but I don't have, they're not the same, right? So they're different, so I would want to take that into consideration and note that. Now I'm going down through and I'm taking a look at my individual cell sizes here, right? 10, 77, 41, 28, right? So clearly different cell sizes here, so wanted to make note of that. My standard deviations, I'm not directly comparing standard deviations, but they're not looking too bad. If I take 8, that's my biggest, and square that to give myself a variance of about 64, and I take my smallest variance, which looks like it's here, which is 6, and square that, 36, 64, they're about 2 to 1, somewhere around there, so it's not huge difference, right? Without doing some screening, just trying to make some decisions about how I might go about things here. But if I go down through and I take a look at my Levine's test, does it suggest that I have reliably different variances across these populations? Alex is shaking her head no, she's correct, right? But going down through and taking a look at our overall model, Lauren, what do we say happened with this model based on our effects here? No worries. So looking at our overall model, our test of our ANOVA table, what's going on in terms of our effects for this model? What's that?
I'm a little lost.
Yeah, there's nothing going on here, right? If we look at our, so we got an effective intercept, which means the mean value across everybody is reliably different than zero, but that's not a terribly interesting thing to have, to note, right? But if we look at our main effective gender, right, we have no systematic differences of positive effect across men and women. If we look at main effective class, we have no evidence of systematic differences, or not no evidence, but little evidence of systematic differences in positive effect across my three different belief classes. It doesn't look as though positive affect across belief classes is dependent on gender at all. And so what do I have going on here? Nothing, right? This is a giant wash. There's literally nothing going on here, which is pretty impressive given the fact that we've got over 300 people, right? I mean, that's actually kind of surprising. Like, it's impressive to, with this size of a sample, to not get anything, right? So positive affect is a bust here. But let's go down through, because we have another outcome. We can go through, take a look at negative affect. Okay. Here, our cell sizes don't change this around at all, so we know we have different cell sizes. And if we go down through and we take a look at our homogeneity of variance, our Levine's test is statistically reliable, suggesting what? We have some concerns about our homogeneity of variance test, right? And if we go up and we take a look at our smallest variance here, relative to our largest variance, right? We can go through and start to take a look at our ratio of what's going on with that. And if we go and take a look at our ANOVA table, Katie, what do we have going on with our ANOVA table here? Okay, what are my significant effects? Okay, so I got a main effective gender, and what's that? What's the for? I got a main effective gender for negative affect, and so what's that telling me?
That negative affect is the
Okay, so because this is a main effect, what are we collapsing across? Steph?
So the main effect is the same, but regardless of gender. The class is negative.
What's that?
The class is a main effect regardless.
Okay, yeah, so we've got a main effective class and a main effective gender, right? So our main effective gender is saying, on average, either men or women are reporting higher levels of negative affect than the other, irrespective of class, right? And how do we quickly and easily make an interpretation of that? Just look at the means for gender, right? I mean, we got marginal means; these are adjusted means, but Angela, what's going to be our interpretation of this main effective gender? Yeah, our women are reporting higher levels of negative affect than our men, at least in the sample, right? Regardless of what class that they are, belief class they're in. We also have a main effect of class, and what does this suggest, Stephanie?
Oh, you asked about gender.
Yeah, oh, yeah.
Sorry. There's also a main effect of class, regardless of gender.
Right. So, on average, people in these different classes are reporting some different levels of negative affect, irrespective of participant gender. Can we make a quick and easy interpretation of that technically? Now, if we look at these means, we can probably guess what's going on. But are we able to go through and make an immediate interpretation, competent interpretation of that for our main effect here? No. Why is that? because I've got 3 different places, right? So there are 3 different ways that this could be, if I just in a pairwise test, that this could be different, right? And so we have to go through and do some follow-up stuff with this. Okay. And then we can go through and we can calculate omega squared and things like that. I'm going to assume that you guys have a good sense for how that's going. Are we feeling comfortable about going through and making just a general interpretation of the omnibus effects for these factorial designs? Cool. All right. Let's go through. Let's take a quick break. We'll come back in and jump into follow-up test stuff. So, went through and talked about main effects. We've got the main effects stuff figured out. But if we get our interaction effects, and let's pretend in the 2x2 that we had gotten a reliable interaction. Our omnibus interaction just says that the effective factor A on our outcome is dependent on factor B. Again, anytime you see the word interaction and someone asks you to interpret an interaction, this is how you interpret it. The effect of this variable on the outcome is dependent on this other variable. If you say that, you'll always be correct, right? Now with our means-based test, we can change this over and say differences across levels of this factor are dependent on this other factor, so vice versa. It's always the same thing. Now, are you joking me? Okay, well, we'll figure this out in some other direction. Okay, now I know what happened, never mind, we're good. So our options then, what we need to do is we need to have some sort of follow-up test to start to tease apart what this interaction looks like. For our main effects with 2 levels, we can just look at the means, right? If we've got a significant main effect, and that statistical test is reliable, we already know what group is significantly higher than the other group just by looking at the actual means, right? But in our interaction terms, it starts to get a little bit tricky because we need to go through and probe this. And so our options, as before, planned contrasts or post hoc tests. What's important here is that thinking about sort of conceptually, how are we going to approach this? Like, what is our conceptual interpretation? If we think about this example that we were working with low, medium, and high arousal levels, looking at performance at either an easy or a difficult task, we found an interaction of task difficulty and arousal. And if we look at our plots, we see that it looks like for easy tasks, performance increases with arousal. For difficult tasks, we've got something that looks like optimal levels of arousal occurring at moderate levels here in the middle. Now, is this an interaction, Morgan? Yeah, how do we tell it's an interaction?
Because we know is, like, first of all, the lines wouldn't be parallel.
Yeah, right. So if we connect a line, right, we've got different things going on at different levels. We've got an interaction. But the tricky thing is, say, do we want to interpret this and ask the question, what's the effect of arousal on performance at different levels of task difficulty? Or what is the effect of task difficulty on different levels at different levels of performance? These are mathematically equivalent. It doesn't matter. You can ask these either way. It starts to become important from a conceptual standpoint. Like, you need to know from your theoretical standpoint often what happens, right? When we're looking at these interaction effects, we'll often have like some type of effect in the literature that we know happens, right? So we know that for groups A, B, and C, there tends to be this difference. This has been replicated again and again and again and again. So probably what I would do is say, if I found an interaction of that factor with another factor, right, I would say, what is the effect of factor A on performance across different levels of factor B, right? Everybody knows that factor A has an impact on performance. What's this other thing? And what do we call that other thing? We tend to think about this more in terms of a regression model. Moderator, right? We've got some third factor that moderates the effect on this other thing. Interactions in ANOVA, interactions in regression, we're always working with moderators. Something's moderating another thing, right? Now, the question is how many different main effects? So what kind of type of design do we have here, Alex? A 2x3. So for this 2x3 interaction, how many different effects do we have that are meaningful? Okay. If we go through and we take a look, if we just want to take a look at effects, right? So how many means do we have? 1, 2, 3, 4, 5, 6, right? We've got 6 different means, right? And we can easily calculate how many pairwise comparisons we have by taking n good night. So you just sit there like, hey, we're going to put up a bunch of markers that don't actually draw on anything. So we got n times n minus 1 over 2. This tells us the number of possible pairwise comparisons that we could make, right? So we've got 6 different means here. So we've got 6 different cells. So we take 6 times 5 divided by 2. How many means do we got? We got 15. We got 15 different possible comparisons that we could make in this graph. That is too many. Are all of those meaningful? Why not?
Let me guess. Because you want us to figure this out priority, so you need to have certain hypotheses.
Well, okay, that would be a perfect thing. But even if we were just doing a completely exploratory approach to this, there's 15 different comparisons we can make. We go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There's 15 different comparisons that we could make across these. Why might I suggest that some of these comparisons aren't meaningful? Does it make sense to compare low arousal and or low performance on a low arousal easy task with medium arousal difficult task? Why not? I'm crossing factors. If I find a difference, like, I don't know, is that a difference because of task difficulty? It doesn't make any difference, right? Like, I can't, it's not a meaningful interpretation. I physically can do it, right? Like, the FBI is not going to show up and take away my birthday if I run that, right? But it just, I can't make any sort of real interpretation off of that, right? And so this is the crux, and this is going to start to become important for trying to develop a strategy for even post hoc tests. So this will tell me how many comparisons I can make. This won't tell me how many meaningful comparisons I can make. Now with a one-way, does this give me my number of meaningful comparisons? Yeah, it does, right? Because I only have one factor, right? So if I have 4 levels in a one-way design, I have 4 factors, or 4 levels to my factor. And so I go 4 times 5, or 4 times 3 is 12 divided. So I got 6 for a factor with 4 levels. There's 6 possible comparisons I can make, and all of those are meaningful comparisons, right? But for our factorial designs, we can't make reasonable interpretations of comparisons that are made across factors because I don't know what to make of that. I can say that they're different, I just don't know why they're different, right? So, for this example here, I can take a look at simple main effects of factor A at each level of factor B, okay? And so the question here is, what is the effective task difficulty at low levels of arousal, right? I can say, what is the task difficulty at medium levels of arousal? What is the task difficulty at high levels of arousal? What's going on here? All my animations are all screwed up. Something weird happened. All right. So what is the effective task difficulty at low levels of arousal? So here, I'm looking at task difficulty at low levels of arousal, so I'm comparing these two here, right? Effective task difficulty at medium levels of arousal, these comparisons here. Task difficulty at high levels of arousal here, right? So I'm looking at the effective factor A at each level of factor B, right? So I've got a difference here, a difference here, and a difference here. So that's 3, right? I can then look at the simple main effect of factor B at each level of factor A, right? So the question is, what is the effect of arousal on performance at easy tasks? Now before we had pairwise tests, but this one, right? Asking you the effect of arousal on performance for easy tasks, I'm doing a comparison of these 3 means, right? So if I'm just looking at easy tasks, I'm saying does low and medium and high differ? I can also ask what's the arousal, effect of arousal on performance for difficult tasks, which I'm going to go here, here, and here. All right? And so what we're doing here is we've got a total of 1, 2, 3, looking at simple main effects at factor A. And then I've got, at level factor B, I've got 1, 2, 3 at low levels, and 1, 2, 3 at high levels. So how many total meaningful comparisons do I have? 9, okay. There's 15 possible that I could make, but only 9 of these are meaningful, right? People see what, because this starts to become important when you start thinking about how do I go through and probe this interaction effect. Okay? So I can ask about the differences in task difficulty at different levels of arousal, which is going to give me these pairwise, or I can ask about the differences in arousal at different levels of task difficulty, which gives me sort of an ANOVA type of thing here, right? And so how we're going to go through and take a look at this is what we would do is for looking at differences in task difficulty at levels of arousal. This is easy, right? These are just pairwise tests. That's not bad. But looking at impact of arousal at different levels of task difficulty, what I would do is start out with what I would call a simple effects ANOVA. So what I would do is I would split this file based on task difficulty, right? So tell SPSS high levels are easy and difficult, and then just run a one-way ANOVA at each one of these, right? And then run a one-way ANOVA at each one of these. See if I have differences there, and then if I do, then just follow up and move forward with that. Okay. Now in terms of linear contrasts, right? We don't have to restrict ourselves to pairwise comparisons. We can go through and run linear contrast just like we did before. Now our value of our contrast, put that together the same way you guys have done before. 95% confidence intervals, same way as we've done before, where your standard error is going to be mean squared error over n. Or here's how SPSS is running things. Use this for running your contrast. This is just easier because it's already going to take into account unequal sample sizes, right? So this is that formula in the slide that I keep promising to send you that I didn't. When you're going through and running contrasts for the current problem set that you have, take a look at this. Run your Fs, run your statistical test the way you've run them before, but in terms of calculating your confidence intervals, go ahead and take a look at this. This is going to make things easier, okay? So your sum of squares contrast, after you got the value of your contrast, sum of squares contrast is easy. This is how you calculate it for unequal samples. Then you've got your F-tests here. This is all just the same stuff that we've done before in your, with the one-way designs. Okay, so we've got sum squares, so your F is your mean squared contrast over your mean squared error. Mean squares contrast is just your sum of squares contrast. Mean squares error taken from your simple effects ANOVA tables.
I think that's taken off the file.
I don't know what happened here.
In the updated Factorial, I have it.
Oh,
Literally took it off the
is this the update? Is this?
I went to the line of like.
Yeah, there should be an updated one.
Is it like, cause it's in the files and is it not in the like lectures? Right. I took it out of lectures.
Oh, did I put it in the wrong place? Go to, where is it? Is it in the handouts?
Announcements?
No.
No, it's in the. I literally just saved it.
Go to lectures. Oh, no, there it is. No, go back. Updated, right here.
Oh, it's above the,
Yeah.
the very bottom one.
Okay,
Alright, sorry.
no problem. Okay. So, for our contrast, we're just gonna run these the same way that we would run our one-ways. But what we're gonna be doing is taking values from our simple effects ANOVA table, okay? And so this is, if we get that interaction, if we got more than two levels to our variable, what we're gonna do is we're gonna split the file by our other factor, and then just run our one-way ANOVAs across our other factor, and then pull our values out of there. And we'll run through an example so you can see what this looks like, okay? All right, for our effect sizes, still gonna use this as the value of our contrast over our error variance. Again, the problem is though, what do we go through and we select as an error variance for our samples, okay? Thinking about our example where we've got task performance across temperature and humidity, right? Taking a look back at that. In our one-way, when we're just looking at task performance across temperature, variability not associated, so our mean squared error for that example contained all the variability in our sample that wasn't related to temperature, right? Because temperature is our only factor. So anything that's not systematically related to temperature, where does it go, Lauren? Into your error, right? And it gets all that calculated there. But, so if we think about that, so total variability, temperature, everything that's not related to temperature goes to error, right? But for our 2x3 design, right, that mean squared error contains variability not systematically related to temperature, humidity, and interaction, right? So in our, for our 2x3 design, our variability of effect contains these three factors. And so what's gonna be, systematically, what's gonna happen to our error term in terms of this related to that? It's gonna be smaller. And if we're just pulling our mean squared error is our error term for our effect sizes, what's that gonna do to our effect size? In our factorial design versus our one-way design. It's gonna make it bigger, right? And so this is what happens. So our mean squared error is systematically lower with our one-way. This is a great thing for power, but it's gonna inflate our effect size. And again, this is always a crux, right? We already know that we're inflating our effect size just by publishing data that is always gonna be reliable, right? And so if we've got systematic factors like our design that are gonna start to inflate, we're always gonna be very concerned about that, making people think these effects are larger than they are. And so HAL documents a procedure that is, I think, good and smart, but going through and taking figures out of your Factorial ANOVA table and adding those things back into your error term in order to create a more appropriate error term for your effect size. The argument being that if we were to calculate an effect for temperature from our one-way design, that effect should still be about the same thing as we would get out of our ANOVA, or out of our factorial design. So what HAL's doing is saying, okay, I want to take a look at my sort of a contrast here for condition, and so for my error term, what I'm going to go through is I'm going to take my sum of squares error, but then I'm going to factor back in my sum of squares humidity and the interaction sums of squares, because those were things that were included in the error term in my one-way design, right? So basically, you're systematically making your error term bigger because we're not just parceling out stuff that's related to my other factors, okay? This is if you go through and are following how this is kind of what he's doing for practical purposes, this starts to, because we can get to this a little more effective if we're running simple effects ANOVAs by just going through and saying, okay, we're going to calculate our effect size for our contrast as our value of our contrast, whether this is the difference between two means or the difference between sets of means, over some options. We can use square root of our mean squared error from Factorial ANOVA. Don't do that. That's going to inflate your effect sizes, okay? But what we could do is take the square root of our mean squared error for our simple effects ANOVA. Because what we're going to do is we're going to split that file by our one factor, and then just run a one-way ANOVA at individual levels of that factor, right? And so what we've done is we're back to where we were before, right? And if we have a balanced design, no problems with homogeneity of variance, then using just the mean squared error, sort of basically the average error term across our cells in our one-way design, that's a reasonable approach to take with this, right? Or if we've got unequal cells, possible violations of homogeneity of variance, more concerns about homogeneity of variance, what we can do is for our contrast, we can take the square root of the pooled variances of our samples that we're sort of looking at in this contrast, okay? Remember that in this scenario, what we're doing is we're saying, all right, I've got mean 1, mean 2, mean 3, and mean 4, right? And this contrast 1 is looking at mean 1 versus mean 3 and mean 4, right? If I've got unequal sample sizes and I've got concerns about violations of homogeneity of variance, what I can do is I can say, well, I'm going to calculate a pooled variance estimate that's going to be equal to degrees of freedom for 1 times variance of 1 plus degrees of freedom for 2, or not 2, 3 times variance for 3 plus degrees of freedom 4, variance 4 over N1 plus N3 plus N4 minus 3. Okay. So I've just taken my pooled variance estimate that I would normally take. I'm just adding terms onto that and sort of making sure that I'm dividing by my appropriate degrees of freedom. And then what I can do is I can take that pooled variance estimate that's just accounting for the groups that are in my specific contrast that I'm looking at, and then just take this, take the square root of that and use that as my standardizer. So that's what we would be doing here. Okay, people see where we're getting this? And then also, if we have some sort of control group, if we want to just sort of basically run a Glasses delta and just do that, we could also do that as well. So again, things that we always want to go through and start taking a note out: have we violated homogeneity of variance? Do we have equal cell sizes? And this is going to start driving sort of where we go with running our different tests. So in general, right, when we're taking a look at our contrasts, if we have balanced design, no clear violations of homogeneity of variance, we might think about running our error term from our Factorial ANOVA table, but in general what we're probably going to do, just to be conservative with our unbalanced designs, possible homogeneity of variance, we're just going to pull from this simple effects ANOVA. And this simple effects ANOVA is going to be, at least for now, it's just going to be a one-way design. Okay? For our effect sizes, some options. If we're not worried about inflating our D, we can just pull our standardizer from the means from our factorial ANOVA as the square root of the mean squared error, but don't do that. Don't mark points off if you do that. Know that some people might, but don't. If we got a balanced design, no clear violations of homogeneity of variance, might just use simple effects ANOVA, sort of the square root of the mean squared error from that, and that would be fine. If we've got an unbalanced design, concerns about violations of homogeneity of variance, pooled variance of the target groups of in interest, or always glasses delta if there's some baseline variance that makes some sense. All right, yeah.
So just to make sure, when we say balanced design, we mean like equal sample size, right?
Pretty equal, right? As long as you got relatively equal sample, because then if you got a relatively balanced design, I mean, you could run things through the pooled variance estimate, but you could also just average the variances, and it's going to give you the same thing if you've got a reasonably balanced design, right? Yeah. So this is if we're using our a priori contrasts, right? But then we've also got this concern with our post hoc, with our factorial designs. Because the question is, how many pairwise comparisons do we control for, right? So in our 2x2 design, how many meaningful comparisons do we have here? What do you think, Katie? How many meaningful comparisons do we have in a 2x2 design? Four, perfect. We got this comparison, that, and that. So we got 4. How many possible do we have? 6, right? We can compare A1 at B1 with A2 at B2, but I don't know why we could do that. We would do that because I can't interpret that. I don't know what's going on, right? Those are means that are there that you could compare, but they're not valid comparisons to make anything on, right? So 4 meaningful in a 2x2, 6 possible, right? What about a 2x3? What do you think, Angela? Yeah, so we got 9, 15 possible, right? So we got, we could go 1, 2, 3, right? And then we go 4, 5, 6, 7, 8, 9, right? So there's 9 possible that we could look at here, 15 total. As we start to get into higher designs, for a 3x3, you've got 18. For a 3x4, you've got 30 possible comparisons. The number of means that you're looking at starts to get really large as your designs get bigger and bigger, right? A 3x4 is not a crazy ANOVA design, but if you have no idea on how that interaction is going to turn out, you've got 30 possible pairwise comparisons that you could, and if you go and make those, then you've got 30 different things to talk about, right? And so the problem is, then if we've got a 3-way design, right, a 2x2x2, we've got 12 possible comparisons here, right? We've got 1, 2, 3, 4. We got 5, 6, 7, 8. And then we got 9, 10, 11, 12, right? If you're just running on a complete post hoc, you've got a lot of different 2x3 on 24, right? So the number of comparable means is or the number of reasonable means to pairwise comparisons is always going to be a smaller number than the possible pairwise comparisons. But even as your designs are starting to get marginally larger, that number of possible comparisons starts to get very, very large. And so from a complete post hoc standpoint, the question becomes, how do I start to manage this without needing something to be significant at p less than 0.00000001 before I can start to claim a statistical reliable effect? So this is the problem. Do not request post hoc tests for your factorial designs through SPSS. Because what SPSS is going to do is SPSS is going to compare for all possible comparisons. So if you just 2-key that 2x3 design, how many comparisons is it going to control for? 15. How many comparisons can you reasonably interpret? So you just got taxed for an extra 6 comparisons that you can't even make and wouldn't even make, right? SPSS doesn't do that. SPSS just says, all right, these are the number of things. And so you're going to get taxed at a higher rate, and you're going to have far more conservative, inappropriately conservative tests for the number of comparisons that you're going to make. And so what ends up happening, you're stacking the decks against you. And don't try and say, well, I just want to be super conservative, because that's being lazy. Control for the number of tests that you're actually going to compare, not just whatever SPSS is going to give you. Okay. People see what the problem is with this in terms of just asking SPSS in a factorial design to give you corrected tests. Okay. So a couple of different things. Howell talks about a modified 2-key approach, which is what I've had people do in the past. And the idea being, so what we want to do is determine a critical t-value necessary to claim statistical significance. So in that screencast, we went through 2-key and kind of what's going on with 2-key. And so if we want to go through and try and take 2-key and bend it to our will to try and look at post hoc tests in a factorial design, what we would do is first determine how many meaningful comparisons we're going to make, right? So in our 2x3 design, how many meaningful comparisons can we make? 9, right? And so we say, okay, I need to control for 9 pairwise comparisons. Then what we would do is try and find a value of R that gives us a reasonable level of protection without going overboard, right? Now if I've got a 2x3 design, how many means do I have, how many cells do I have in a 2x3? 6, right? And if I set R to 6, it's gonna, how many means am I gonna compare for at R equal to 6? 15, right? Now I don't want 2-key to correct for 15. What I want to do is try and set R so it gives me something as close to 9 as possible. So with 9 meaningful comparisons, I can set R equal to 4, and that's going to control for 6. That's probably not good enough, right? If I set R to 5, that's going to correct for 10. 10 is pretty close to 9. It's a little too conservative, but what I could do is in my 2-key table say, okay, what I'm going to do is I'm actually going to set R equal to 5, because that's going to correct for 10 comparisons, which I'm okay for, right? And so maybe I'm going to set in my 2-key table, I'm going to say set R equal to 5 at alpha equal 0.05. Now if I wanted to, I could say, well, I'm going to set R equal to 4 at alpha equal 0.01. That might be a strategy, right? I'm correcting for less tests, but I'm going to set my alpha level as something more stringent, right? So this would be something to play around with. Then what we would do, let's say, so we set R equal to 5, we set correct for 10 and alpha equal 0.05. Then what I'm going to do is find my Q critical based on my chosen R in degrees of freedom, right? So again, thinking back to that screencast we watched, you get our Q critical, and then take that Q critical to get a critical T value based on this correction for 5 tests, right? Remember that Q has a direct relation to T, so what I could do if I found that T critical or Q critical value to be 3.2 or something like that, I could take that 3.2 divided by the square root of 2 to get a new critical T. And then what I could do is just run through and run independent sample T tests, all 9 of my independent sample T tests, that I could take a look at any of those tests that exceeded my modified critical value, I could say is statistically reliable at a modified 2B whatever. Okay, so if you've gone through and watched that screencast about 2-key and how that's going through and being calculated, this is something that you could go through and strategically use if you are hard up to use 2-key. Okay, but at the end of the day, this is really kind of getting close enough, right? and it's kind of a complicated thing to explain to other people if you need to explain it to other people. It is not providing very precise control for your stuff, okay? But we're sort of stuck if we want to run post hocs in a factorial design, because the number of meaningful comparisons we have is always going to be smaller than the number of possible comparisons we have, and our post hoc tests are going to correct for the number of possible, not the number of meaningful that we can. Now, something that I'm starting to become very fond of, because I think it's a nice alternative and does a nice job of correcting for this, is Howell talks about a Benjamini-Hochberg approach that's a little bit different, right? With our typical post hoc test, we're worried about family-wise error, right? This idea of compounding error based on the number of tests that we're correcting. This Benjamini-Hochberg takes a little bit different approach. It's worried about the number of false discoveries. So if our family-wise error is concerned with the probability, what's the probability of committing one or more type 1 errors, and saying that if we make even one type 1 error, this whole set is bogus. Benjamini-Hochberg says, what percentage of my significant effects are actually false positives, right? And so what this approach does, and Howell goes through and talks a little bit about sort of the statistical theory behind running this, but the actual procedure for doing this is pretty slick. With Benjamini-Hochberg, what we do is determine a successive critical p-values based on this formula here, right? So say we've got in our 2 by 3 interaction, right? How many meaningful comparisons do we have? 9, right? So what we would do is, so we say, all right, we've got 9 tests. What we're gonna do is we're gonna run all 9 of those tests, but my p-value for each successive test is gonna get more and more stringent. And we determine that p-critical by taking I as the index test, which is the order, divided by k being the number of tests, multiplying that by whatever our alpha is, 0.05. And so what this would look like in our 2 by 3, we've got 9 different pairwise comparisons, right, that we can't make that are meaningful to interpret. If we letter these A through J, is that right? Is J the 9th letter of the alphabet? A, B, C, D, E, F, G, H, I. Oh, okay. It's I, so we don't actually have a J. Pretend that's I. What we would do is make all of our contrasts. So we run all of our pairwise tests, right? And then what we're going to do is we're going to order these from my smallest t-value to my largest t-value, okay? And the order, that's going to be the index, right? So what we're going to do for this first one is clearly not significant even at sort of normal. A test of -3, -0.35, a p-value of 0.726, but this is index 9, right? And so I'm going to go 9 divided by the number of tests I have is 9. So 9 divided by 9 is 1 times 0.05. My p-critical for this test is 0.05. Well, that didn't make it, so we would count that as not statistically reliable. My next highest t, 1.768, associated with p-value of 0.086. This is 8 in my index. 8 divided by 9 times 0.05 gives me 0.044. Still not reliable, right? Here, we get something that's comparable or statistically significant at the per comparison error rate. My next one, a t-value of -2.121, p-value of 0.041. This is significant at per comparison error rates, but what I'm going to do is this is index 7 divided by 9 times 0.05. My critical p at this level for my third test is 0.039, so I'm still not there, right? And we continue on and go down through until we get to our fourth comparison associated with p-value of 0.081. By this time, our critical p 0.033, continue to go down all the way until we get to our very last p-value, right? And so every comparison from this point down is exceeding my critical T, or my critical P, unless this one was like negative 2.476, and then that probably wouldn't exceed, and then we would say that one's not reliable, but maybe the next one is, okay? So what's nice with this is we don't have to fool around with trying to find an R from Tukey that's going to correspond. We can just say, these are the number of tests that we're going to make in this comparison. This is the comparison test that we want to correct for. We're going to run all those pairwise comparisons, line them up, and then calculate a critical P for each one of those as those T's get successively larger. The critical P is going to get increasingly smaller. And so what we would do is then interpret as statistically reliable those tests with p-values that are smaller than our critical P. Okay? People see how this Benjamini-Hochberg test is set up. And this is nice because we can go through and correct for any number of tests. But if we were to Bonferroni correct for 9 different tests or something like that, we get down to some ridiculous value, right? And so that's not great. And even if we were to go through and Tukey for this, that would be very difficult. But this approach is taking a different approach to this. So the question isn't I need to control and make it unlikely that I'm going to make at least one type 1 error. This is saying, what's the percentage of significant effects that are likely false positives, correcting for that and taking a different approach. This is nice. This is, I think, what I'm going to start using in my work moving forward. This is what I'll have you guys do moving forward. Questions on this? Very exciting. Thumbs up. Very happy about this whole procedure. It's going to make your lives easier than trying to go through and figure out where we're at in terms of managing stuff with Tukeys. Okay. And then we got higher order designs, 2x2x2s, right? Sort of teasing some of that stuff apart. We won't worry about that too much right now. Okay. All right, let's jump back in and run a couple more examples with our data. So pull back up your 2x3 or your 2x2 expressive behavior example here. So remember that when we left off, let's pretend that we've got an interaction. Remember that in this design we went through, and for our univariate, here we had expression rating, blah, blah, blah. Okay. We found that here we've got relatively equal sample size, cell sizes, right? But we have violated our homogeneity of variance, right? So we want to be thinking about how we're going to go through and address this. We found that we have 2 main effects, right? And those main effects are easy to interpret because we only have 2 levels to that factor, right? But let's say that we have an interaction term. As soon as that interaction comes up, we've got to do something a little bit different, right? Because we can't just sort of eyeball things and make a determination on what's different than what. What do we always do when we get an interaction effect? What is the first thing we want to do? Plot it. Always want to plot this out first. We want to see what this interaction is looking like. And so if we plot this interaction, as we have in your handout here, we see that we've got depending on how we want to take a look at this, we can examine the difference in express condition at sadness and levels of amusement, which we could do Or we could flip it around if we wanted to and look at differences in film across levels of, condition, either way, okay? What we want to do, let's pretend that before we went into this, we said, we expect that the impact of expressive inhibition the impact of inhibition on expressive behavior is going to be larger for people watching funny stuff as opposed to sad stuff. Okay? If that's the case, then this is what we're going to need. These are going to be the two comparisons that we make, right? If that was our a priori hypothesis coming in, we're going to compare here and we're going to compare here, and then make that take that approach. Okay, so always want to go through, plot this out first, and make it based on your research question. Decide how you're going to go about probing this. But then what we can do with this approach is we want to take a look at differences in our inhibit and express condition for people who are watching an amusement film and people who are watching a sadness film. Okay, so what we're going to do is we're going to split our file and then run some t-tests. What do we want to split our file by? Film, right? Because what we want to do is we want to look at the difference between the people who we told to inhibit expression and we told to just naturally express for the people who were watching the humor film and the sadness film. And so what we're going to do then is go to data, split file, and we're going to split by film, okay? So this is going to give us different t-tests for people who watched the sadness film and people who watched the humor film. I'm going to hit OK, and then we'll go analyze, means, independent sample t-test. We're going to look at instruction condition 0, 1 across, and our outcome is our expression rating here. And if we hit OK, we've got ourselves squared away. Okay. If you look in the last page of this, we've gone through and we've taken a look at, in this 2x2 design, we're looking at the difference between inhibit and express for people watching the sadness film. First one, the sadness film. Yeah. Okay. So we're looking at inhibit express across individuals who are watching the sadness film, and inhibit and express across people watching the amusement film. Okay. If we take a look at our Levine's test for our sadness, so we got a statistically significant Levine's test, right? We know that we have violations of homogeneity of variance, right? And so which one of these lines are we going to interpret? Equal variance assumed or not assumed? Not assumed, right? But it doesn't really matter. We're still clearly statistically reliable here, right? So we've got our, what we wouldn't want to do is start pulling terms out of our Factorial ANOVA because we've got violations of homogeneity and variance. So what we're going to do is just we're going to run some t-tests at this level to go through and start to pull apart this interaction effect. So we see that individuals who are instructed to express their emotion are reporting greater levels of indicating evidencing greater levels of expressive behavior than people who are told to withhold, kind of what we would expect, right? And we see a statistically reliable effect. What else would we want to calculate for this task here? think, Katie? So we see that they're statistically different. What else would we, or there's a reliable difference, what else would we want to calculate here? What do you think, Stephanie?
The effect.
An effect size, right? And what would we calculate as our effect size here? What would we use as our standardizer? I'd probably use a pooled variance estimate, okay? I mean, I've got unequal, sort of relatively similar sample sizes, but I've got violations of homogeneity of variance. So probably what I'm going to do is I'm just going to calculate a pooled variance estimate, take the square root of that to get my pooled standard deviation, and just calculate my effect size for this pairwise contrast. Right? So then I do that, and I see whatever that is, and then drop down, take a look at my my comparison and my amusement condition. What do I have going on here, Alex? For my comparison and my amusement film.
Expression
Yeah. So my people who are I've allowed to express or reporting are demonstrating higher levels of expressive behavior than those who aren't, right? It's statistically significant, just the same as it was before up here, right? But again, we've got a difference of about a full point here versus less than half a point here. What's likely going to be, so how my effect size is probably going to compare? Probably going to have the larger effect size here, right? And if my approach to this was that I'm expecting larger, more dramatic differences in my expression or my instruction condition for people watching the humorous film versus the sadness film, might be able to go through. They're both statistically reliable. They're both different, right? But it looks to me like what's going on is I've got where this difference is coming from is I've got a larger effect for my, or the argument I'm going to make is that I've got a larger effect for individual is in my amusement film as opposed to my sadness film. Okay. Now, I could also go through and split the file by instruction condition and then compare people watching sad and humorous films at natural expression and comparing sadness and humor films at the withhold condition and take a look at that as well. But, and I could do that if I just wanted to run all four of those effects itself, right? But from a 2x2 design, we're still at a fairly reasonable number of effects here. Okay? You'll kind of see how we might go through and tease some of that apart. All right. What if then we go through and pull up instead our trauma beliefs set here. Okay. Remember that here we're going to look at negative effect. So do we have an interaction effect here? What do you think, Angeline? Do we have an interaction effect here when we're looking at this 2x3? So relief class by gender? No. we've got a main effect of gender. Do we need to do any further probing to determine what's going on there? No, there's just two levels, right? We can go up and take a look at the mean level of negative affect for women against men, right? And we see that women are higher, right? So we know that by definition, women are reporting statistically significant higher levels of negative affect in this sample than men. What would we use probably as our standardizer for our effect size? What do you think? I probably just use variance, pull variance for those. I just probably just a hedges G, right? Going through and taking a look at that now. I've got so also I have this main effective class. Can I just determine what's going on with this main effective class? No, right? So what do I need to do then? Probably is I'm going to go drop back down and run a simple effects ANOVA to try and probe some of this stuff out, right? So what I'm going to do, I'm going to go analyze. Now, I could maybe start running contrasts by hand based on my overall mean squared error in this table, but why might I be concerned with that? I've got different numbers of people in each one of my cells. I've got violations of homogeneity of variance, right? And so just taking this overall average error term and using this in my follow-up test isn't going to be responsible, right? I can't do that because I don't have confidence that that's going to be a reasonable estimate for what I'm going to do, right? So what I'm going to do is I'm going to run a simple effects ANOVA here, where I'm going to go through and go to compare means, one-way ANOVA, right? And I'm going to want to take a look at the difference in class for negative affect, right? Because that's what I'm looking at. We don't have an interaction, so we don't have evidence that differences in negative affect across class are different for men versus for women. And what I can do here to save myself some time is say I'm going to go through and just have SPSS calculate my contrast for me, right? So I'm going to go to one-way ANOVA, differences in class, negative affect, my contrast here, and I'm going to say my negative is larger, my negative classes are going to be reporting higher levels of negative affect than the combination of my other two classes. So what's my first weight here? What is it? Oh, so here to take a look at negative 0.5. Yeah, negative 0.5. What's my next weight? Negative 0.5. Oh, I hate this thing. 0.5. And what's my last weight? 1. Add there. Okay. Continue. And the script is homogeneity variance, my Welch test. Continue here. And hit OK. All right. So what I've done now is I know I have a main effect of belief class on negative affect that's not dependent on gender. So what I've done is said, okay, what I'm going to do then is I'm going to run a one-way. My follow-up test here is just going to be a one-way ANOVA, just looking at negative affect across belief class for the full group of folks. Okay, and so what I've got is that I find out that for belief class, I've violated my homogeneity of variance, right? And so I've got, what this is suggesting is that variability in negative affect across these populations of these three populations is different, right? And so I want to be thinking about that. So if I go down through and I take a look at my overall ANOVA table, I see that I do have evidence of differences across my three groups, right? But is this what I should be looking at if I violated homogeneity of variance? No. Probably looking down at my robust test. My Welch's is actually not reliable, but again, at the end of the day, I'm going to ignore these two things because I've already found that I have a significant main effect of belief class based on my overall factorial design, right? And so this is just for my follow-up. But I do note that I've violated homogeneity of variance, right? And so if I go down through making sure that I've coded my things, so I've got interpersonal, benevolent, negative here, right? And if I go down through and I take a look at my contrast, which one of these am I going to be focusing on? Yeah, equal variance is not assumed, right, because I violated up there. But I can go through and see here I have value my contrast, my standard error, my test statistic, my p-value here. I've got this all put together, okay? And if I wanted to calculate a effect size, how would I go about it with this contrast here?
The pool variance?
What's that?
The pool variance?
Pooled variance, exactly. And where would that pooled variance come from?
The contrast test.
Yeah, right. Remember, because we got three groups here, right? So we can't just, before when we were on just pairwise stuff, we just sort of run our pooled contrast. Here, or pooled variance, here we've got three groups, right? So we can still run a pooled variance, we just have to add on this extra piece here, right? And so what we could do is we could go through and take the variance of each one of our groups and sort of weight that out using our pooled variance formula and calculate that just based on this, right? What if we wanted to calculate a confidence interval around this? Is that hard to do? What do you think, Katie? Do we have enough information here to calculate a confidence interval? Yeah. So what do we need for a confidence interval? We need a point estimate. Got a point estimate. We need a standard error. We got a standard error. And now we just need a critical T, right? And now we could calculate a critical T based on probably, if we wanted everything to match up with 100 degrees of freedom, right? We've got an adjustment here, right? We just want to say what the degrees of freedom for the critical T value was. In general, without any correction, our degrees of freedom is 330. With the correction, it's about a 100, right? So I might choose a critical T with 100 degrees of freedom, drop that in to calculate my confidence interval around these means. Okay. So again, this is nice because we've kind of run into a problem. We've got different cell sizes. We've got different variances. And this starts to get complicated to grind this stuff out by hand. But if SPSS will do it for us, let's have SPSS do it for us because it's going to give us more appropriate corrections than having to go through and do it longhand. So unless I'm telling you specifically to do this by hand, do whatever you can in SPSS. Okay? All right. You guys are champions. Folks, thank you